Hello, and welcome back to the course on Physics for Engineers. So we are now on chapter 11 of our course, which is on electrostatics. So before we proceed with the first lesson, let us first review some concepts. So in your course on mechanics, you have discussed about the four fundamental physical quantities. They are length, mass, time, and charge. So in this chapter, we will be focusing on the fourth fundamental quantity, which is called electric charge. So for the first lesson, we will be talking about what is the relationship between the electric charge, the electric field, and the electric force. So electric charge is the property of matter involved in electromagnetic interaction. So it can be positive, negative, or neutral. The rules or the law of electric charges states that like charges will repel and opposite charges will attract. So if you have two positive charges, they will repel each other. If you have negative charges, they will also repel each other. And only a positive and a negative charge will attract with each other. Only opposite charges attract. So the symbol for charge is Q. It can be a small q or capital Q. And its SI unit is Coulomb, named after Charles Coulomb. So matter is composed of atoms. So we are all composed of atoms, and atoms are further composed of subatomic particles called electrons, protons, and neutrons. So protons and neutrons are in the nucleus of an atom, while the electrons are orbiting around the nucleus. An electron is negatively charged, a proton is positively charged, while a neutron has, from the word neutron, so it's neutral, it has no charge. So furthermore, proton and neutrons are composed of a more fundamental particles called quarks. So when an atom gains or loses an electron, that atom becomes ionized. So when it gains electrons, it becomes an anion, and when it loses an electron, it becomes a cation. So cations are positively charged, anions are negatively charged. So you have learned that in your chemistry. So the atom that loses an electron becomes positive, and the atom that gains an electron becomes negative. So charges interact with another or communicate with one another by virtue of their electric fields. So charge is the electrical analog of mass in mechanics or in gravity. So the electric field is basically just the imaginary field generated by an electric charge, and it is analogous to the gravitational field, where the gravitational field is just an imaginary field generated by a mass m. So if you have a point charge, by the way, a point charge is just a charge which has no physical properties. It's just a point. It has no width, it has no length, it basically has no size. It's a point. So if you have a point charge Q and it's positive, the electric field is pointing away from the point charge. The direction of the electric field is always along the line connecting the charge and the point where you want to find the electric field. So at this point, the electric field is pointing away from the charge. If you have a positive point charge. If you have a negative point charge, on the other hand, the electric field is always pointing towards the point charge. So take note, the electric field is a vector field. It's not just a single vector, it's a set of vectors. So take note, this is a vector pointing in quadrant 4. This is a vector pointing in quadrant 2. This is a vector pointing to the negative x-axis. So it's a collection of vectors. It's a field. So again, direction of the electric field is along the line connecting the charge and the field points. We should usually call these points where we want to find the electric field as the field points. So as I've mentioned earlier, charges communicate with other charges through their fields, and their fields actually exert a force on other charges. So if you have a point charge Q and you place it in an external electric field, so this electric field could be due to another charge, then this charge Q will experience a force equal to the charge times the electric field. So this is now the relationship between electric charge, electric force, and electric field. So in the case of positive charges, you will notice that the direction of the force is just the same direction as the electric field if Q is positive. On the other hand, if Q is negative, then there's a negative sign, so negative of a vector is antiparallel. So meaning the force on a negative charge will be opposite the direction of the electric field. So a positive charge moves along the direction of the external magnetic field, while a negative charge moves in the direction opposite to the field. So if you go back to the point charge, so this is the electric field of a point charge. Now, if we place a negative charge at this point, we know that the electric field due to the point charge Q is in that direction towards the negative x-axis. Now, if we place a negative charge there, then the field at that point will exert a force on this negative charge. And since negative charges move opposite in the direction of the field, so the force will be in the opposite direction. And this is the reason for the attraction between unlike charges, between a positive and a negative charge. Now, how about I place another positive charge in this at this point? So I know that the direction of the electric field at this point is towards quadrant 1. And since this is a positive charge moves along the direction of the field, then the direction of the force will be also in that direction. And this is basically the explanation for repulsion, why two positive charges repel. The same thing also happens with two negative charges. So this force here is the force exerted by the electric field of this charge. But this negative charge again has its own electric field, meaning it will also exert a force on this charge here. And the force is actually mutual. They have the same magnitude but opposite in direction. So this Q here this positive charge here will pull the negative charge toward itself, and the negative charge will also pull the positive charge towards itself by virtue of Newton's third law of motion. For every action, there's always an equal and opposite reaction. So if you now have a collection or a distribution of charges, and you want to find what is the total force on a charge Q due to the neighboring charges Q1, Q2, and Q3, then the total force obeys the principle of superposition. So the total force is just the vector sum of all the individual forces acting on Q. So you have force exerted by Q1 on Q, the force exerted by Q2 on Q, the force exerted by Q3 on Q, and so on, depending on how many charges are there that is acting on your charge Q. Now, if you wanna just find the electric field at the location of Q, then the principle of superposition also holds. So the total electric field, for instance, at the location of Q, at this location, is just the electric field due to Q1, Q2, Q3, and so on, depending on how many of them are there. And the relationship between the total electric force on Q and the total electric field at the location of Q is given by this one. So we have presented actually this equation earlier, but it's in terms of force. Force is equal to QE. Now E is equal to force over Q. So from here, I will now present to you or define now the unit for electric field. So force has a unit of newtons. Q, the charge, has a unit of coulomb. So therefore, the unit of electric field is newtons per coulomb. Okay, let's have an example. So we have a proton. The charge of the proton Q is equal to E. So E is what we call the natural quanta of charge. This is actually the charge of the magnitude of the charge of a proton and an electron. So a proton has a charge positive E, an electron has a charge of negative E, where E is equal to 1.602 times 10 to the negative 19 coulombs. So the mass of the proton is 1.67 times 10 to the negative 27 kilograms. And this proton is placed in a uniform external electric field directed towards the positive y-axis. So it has a magnitude of 2 Newton per coulomb, then direction of J hat. So find the force exerted on the proton by the field. How strong is the electric force as compared to the gravitational force on the proton? Okay. So we just use the formula for force, given the charge and the electric field. So it's just Q times E. So we have Q, the charge is E, which is 1.602 times 10 to the negative 19 coulomb. And the electric field is 2 Newton per coulomb J hat. So therefore, we have 3.20 times 10 to the negative 19 Newton and J hat. So the force is in the same direction as the electric field. It's in the J hat direction. Now, how do you compare now the electric force and the gravitational force? So we just take the ratio. So this is the electric force. So we already know the electric force is just Q times E. So this value, this is the magnitude. And the magnitude for the gravitational force. So in our case now, for our Q, positive charge Q, the proton, there is an upward force acting on it due to the electric force, and there is a gravitational force acting on it downwards. So there are two forces. Take note, gravitational force is always directed downwards, and it has a magnitude of m times g. So we know that Q times E is this one, 3.20 times 10 to the 19 Newton. We know the mass of the proton, and we know the G is just a constant, and this will give you a value of 1.96 times 10 to the 7. So 1.96 times 10 to the 7, that is actually approximately 2 times 10 to the 7, or 20 million times stronger. So no need to take into account gravitational field when you are trying to find a gravitational force, when you are trying to solve for electric forces, because gravitational forces are negligible when you compare it to electric force. As you can see in this example, it's 20 million times stronger than the gravitational force. So let's have this example. Suppose an electron, where the charge of an electron again is negative E, is placed in a region where there are superimposing electric fields. So it's placed at a point where the electric field at that point is due to, say, two sources. Say, there's an electric field E1, 2 Newton per coulomb J hat, and there's an electric field E2, 4 Newton per coulomb I hat. So what is the total electric force on the electron? So in this case, we we follow the law of superposition. So the total force is just equal to force due to electric field 1 plus force due to electric field 2. The force due to electric field 1 is Q times electric field 1. The force due to electric field 2 is Q times electric field 2. So you factor out Q, and then you just have E1 plus E2. Where E1 plus E2 is just the total electric field. So the total electric force is just Q times the total electric field. So you can also do directly use this equation. So this is just the total electric field. So this will give us a value of Q is negative E, so that's negative 1.602 times 10 to the negative 19 coulomb. E1 is 2 Newton per coulomb J hat. E2 is 4 Newton per coulomb I hat. And we will write this vector in terms of standard form, and we get a value of negative 6.4 times 10 to the negative 19 Newton I hat minus 3.2 times 10 to the negative 19 Newton J hat. Take note, you cannot add different vector components, okay? You can only add same vector component I hat and I hat, J hat and J hat. So this is now the vector, the force vector. Okay. So if you will notice, this force vector has all negative x and y components. I hat is the x component, it's negative. J hat is also negative. So which means it is in quadrant number 3. Can we verify this one? So this is an electron, and this is electric field 1. It's in that direction. We know that negative charges move in the opposite direction as the electric field. So meaning F1, the force due to electric field 1, will be in the opposite direction as E1. And in the case for E2, it will also be in the opposite direction as E2. So in this direction. So this will be F2. So you add these two vectors using parallelogram method, and you get the total vector in quadrant number 4. So that is now the total force vector. Now, if you want to get the magnitude of this vector, then just use Pythagorean theorem, square root of the x component squared plus the y component squared. Sorry. And you will get a value of 7.2 times 10 to the negative 19 Newton. If you were asked for the direction theta of this vector, so the direction of this total force vector is just this direction. We usually measure our direction or angle from the positive x-axis and then counterclockwise. So this is our direction theta. And we can obtain theta by just taking the tangent inverse of the y component over the x component. Now, this is very tricky if you are working with vectors in quadrant 2 and quadrant 3. If you are working with vectors in quadrant 2 and quadrant 3 and take the tangent inverse of their components, you will not, but your calculator will not give you the correct answer. But always take in mind that there are always two values of theta or angle that has the same tangent, the same sine, and the same cosine. So in this case, your calculator will only give you this angle, 26.6 degrees. But this is wrong because 26.6 degrees is in quadrant number 1. Take note, quadrant number 1 has angles from 0 to 90. Quadrant number 2, 90 to 180. Quadrant number 3, 92 to 270. So, meaning, since our vector is in quadrant 3, we expect that our angle must be between 180 and 270 degrees. So, to get the second angle, you just add by 180. So, 26.6 plus 180, you get 206.6. And this is now the correct angle. So take note, your calculator can only give you one value for tangent. And it's up to you to determine whether that is correct or not, depending on what quadrant your vector is located. Okay, so that ends this lesson. So for the next lesson, we will be discussing how to calculate the force and the electric field given the force and electric field of a point charge. And we will do that by using a technique or a law called Coulomb's law. I will see you again in the next lesson.